Hi everyone, today I want to give a short introduction to the derivatives and its application, linear approximate. We all know that for a derivative to exist in multivariable calculus, this formula must be satisfied, which is the fa plus h minus fa minus lh. This lh is actually a linear mapping, and it is basically the derivatives times a minor change happening in the pre-image. We say pre-image is the input of a mapping, which is a function. We let it to be n-dimensional input, and we can map it to m dimensions. It could be higher, it could be lower, but if we said the derivative exists, then it is differentiable. So what is linear approximation? Well, I have to say that when we are dealing with a nonlinear function, it would be very hard for us to manually calculate the value of that function. For example, suppose you want to calculate. When we use it as an input, can you directly calculate the value of .000123 square? It is so hard for you to directly calculate it unless you have a calculator. Well, if you want to get the exact value of this expression, I think you have to use a calculator, but we can approximate it using linear approximation. What is the linear approximation? For example, look at these two graphs. A linear approximation is to use the derivative as a part of the expression, the derivative of f at a times the small change happening in the pre-image plus the value of f at a. This is a simulation to the behavior of this nonlinear function, and when the change is small enough, the difference between the simulated value and the real value of the function will be small enough that the error between the two values will be negligible. So, to carry on, we have to calculate the derivative at a, and this linear approximation is to use a linear function to simulate the behavior of this nonlinear function around a neighborhood. And that neighborhood is this a. Back to the question, suppose we want to calculate this value. We know that 4 squared is equal to 16, which is, so if we want to calculate this value, the easiest way is to first use the derivative of this function, which is when x equal to 4, 2x is equal to 8. So we now have the gradient of the function at x equal to 4. When x equal to 4, fx is equal to 16. Let's take all the values into the expression. We have h this minor change equal to x minus a, in which this a is 4. So how should we use it? We take this into the expression plus 4. This is equal to so this is the amount of change happening in x when x change 0.000123, y will change this amount. So we could approximate that when f at 4.000123, the value will be very close to 16.000984. When we use a calculator, the difference between this value and this value is only this 0.2, which is so small. We could conclude that the linear function we designed could simulate the behavior of f equal to s squared well enough around this neighborhood of x equal to 4. So after all these calculations, let's go to the geometric view. In our definition, we already know that limit fa plus h minus fa minus lh divided by the norm of h. When h is close enough to 0, the limit of this expression would approach to 0. So, what does this expression actually means? The actual value would be 4.0004. If we use the linear approximation like the way I mentioned above, the answer would be 4.0002. You can see that the error between the real value and the value we use a linear function to approximate is 0.0002. Compared to the one above, this is much bigger. Why is that? Well, we can see that the h over here is so much more smaller than the h over here, in which this is equal to 0.0002. This is equal to the amount of change happening in the pre-image, which is also known as x. For this one, we have 0.000123. We put them together. You can see that this is smaller than this one. We could also conclude that. So why is that? Why is the error between these two different values different? Let's view it in this graph. When we say that derivative at one point is actually the gradient, as we all learned, whether it's in high school calculus or in the first year of university level. For example, over here, when f is equal to a, the derivative of f at this point is equal to the gradient of this tangent line. When we want to approximate that when f is equal to a plus h, when the h is this big, the gradient plus the value of h times the derivative of a at this point plus the actual value of f at a is equal to this. But in fact, for this nonlinear function, the real value of f a plus h is over here. The difference between the real value and the value we use in linear approximation is this error. However, like when the h is so small that we can find that the amount of change between y-axis and the amount of change between x-axis, when we zoom this, it would be something like this. This is the error between the f a plus h and f a plus f derivative times h. When we keep decreasing the value of h, when the h is small enough, the amount of the error will be smaller and smaller, and eventually at this neighborhood you can see that the gradient of this nonlinear function and this linear function is almost the same, and this would simulate the behavior of this nonlinear function well enough. So even that they are still different, the difference is small enough. So this is my interpretation to the linear approximation. And in terms of the definition of derivative and the differentiability in the multivariable calculus, here this linear mapping represents the derivative of f at a times h. For derivative, it is actually delta y delta x, and the delta x is equal to h, which x is equal to a. Let's assign a to x, and a could be a vector, could be a scalar. It depends on the space it is situated in. If it is in a real valued function, then it is a scalar. But if it is in a higher dimension, like 3 dimension or even higher, it is actually a vector, and the vector has direction. Scalar is only a value, which is something that you should notice. Over here, when we times x to this expression, we would get the amount of change in y, which this is actually the ratio between the amount of change in y divided by the amount of change in x. By definition, and this expression times h will be equal to this. The expression of this would be equal to 0, and h is, and for h, though that h is infinitely close to 0, it is still larger than 0, and thus this expression is larger than 0. And sum a value that is larger than 0, use it to divide 0, the answer would be 0, which is the definition of differentiability. This exists, and we can use it to prove differentiability. The meaning of this expression is when the amount of change happening in X is small enough, the linear approximation we use to approximate this behavior would be accurate enough to predict the value of the function after the change in the pre-image. So this is my first video demonstrating a concept. I think there is a lot for me to do and a lot for me to just trying to explain more clearly, but I hope it helps. Thanks so much for watching.